Good day, I'm Maile Madziba. Welcome back to our channel. We are continuing with class test 1 and we're looking at part 4 of class test 1 of 2011 of our CIR 123 module, which is a second chemical engineering module at the University of Pretoria. The second question of the class test says, the table shows the solubility data for sodium carbonate in water, and it also highlights that you can interpolate linearly if required. Now it continues to say a raw material contains 80% sodium carbonate, 10H2O, and 20% inert solids, which are insoluble. It goes further to say the raw material is dissolved in fresh water to give a saturated solution at 17 degrees Celsius. So I made an illustration here. We have the raw material, which is 80% Na2CO3, 10H2O plus 20% inert solution, and it's mixed with fresh water to give a saturated solution of Na2CO3 at 17 degrees Celsius. It's important to understand that even in this saturated solution, we still have the inert solids, the insolubles. Now it goes further to say that the solution is passed through a filter to remove the inert solids as a wet filter cake. Here is it. The saturated solution is fed to a filter, and the wet filter cake or the inerts in a form of a wet filter cake are removed. And then it goes further to say that it says the filter is passed through a filter to remove the inert solid as a wet filter cake. And it says the clear liquid from the filter is treated with phosphoric acid, which is H3PO4, to produce disodium hydrogen phosphate. There is an unbalanced equation there. And now it goes further to say the phosphoric acid is charged to the reactor as a 40% solution of H3PO4 in water, right? This is it. Now after the filter and removing the filter cake or the inert, the clear water, the clear Na2CO3 in water is charged to a reactor and reacted with H3PO4 in water, and the charge of the H3PO4 is actually 40% H3PO4, and that means there's 60% water. Now it also says that the charge is stoichiometrically correct, and also the CO2 is removed from the reactor as a gas, and also highlight that the reaction goes to completion, and also the product stream contains only dissolved Na2HPO4 and water. So for the sake of for part 4, we won't really need much of the other information. We'll look at it in our part 5 and part 6. So for now, I think the first part of the information will be enough. Now let's go to the question. Now the question says, how much fresh water must be added to 100 how much fresh water must be added to 1000 kilograms of Na2CO3 10H2O raw material to produce the saturated solution at 17 degrees Celsius. Now when we look at this, we realize that they are asking us how much of this fresh water is it going to add up with 1000 kilograms of the raw material to produce the saturated solution of Na2CO3 in water at 17 degrees Celsius. So that is actually the question. So it's a little bit longer question, but then I have 5 steps to it. So the very first step that I want us to look at is, let me just write step 1 here. Let me just write step 1 here. So step 1, we're going to need to calculate the mass fractions of Na2CO3 and HO2 in this compound. Remember, we have this compound here. They say the raw material contains 80% of Na2CO3, 10H2O. So the first step, we're going to calculate the mass fractions of both Na2CO3 and also H2O in this compound. It's important to understand that the mass fraction that we're calculating now is not necessarily the mass fraction of Na2CO3 and the mass fraction of water in this whole raw material, but it's rather the mass fraction of Na2CO3 and water just in this compound, in the Na2CO3 10H2O. It's important to notice that. So we'll do that. So step 1, let me just write it down. Calculate the mass fraction of Na2CO3 and H2O in Na2CO3 dot 10 H2O. So yeah, so now going about calculating that, let me just write here that mass fraction. Let's start with the Na2CO3. Mass fraction Na2CO3 is equals to, remember, because it's a compound like this, we're going to actually use the molar mass. So the equation will be the molar mass of Na2CO3 all over the total molar mass, or the molar mass of Na2CO3 plus the molar mass of H2O, right? So yeah, this is actually the total molar mass. So now when you do that, we know from the periodic table, if you do the calculation, that the molar mass of Na2CO3 is actually 106 all over. Now the molar mass of, is a repetition there, the molar mass of Na2CO3 plus, it's important to highlight, to understand that, remember, the molar mass of H2O is actually 18, but there's a 10 here, so which means we multiply the 18 by 10. Is something that we did also in our CIR 113. I think by now it should be a little bit more clearer. So we have 180. Now if you use your calculator, it gives us 0.37063, and that is actually the mass fraction of Na2CO3. Now for water, we can say mass fraction H2O is equals to the molar mass H2O all over the molar mass H2O plus the molar mass Na2CO3, which gives us the molar mass of H2O is 180 all over 180 plus 106. Now if you use your calculator, it gives you 0.62937. Now this is actually our step 1. So with this, we are done with our step 1. We've managed to calculate the mass fractions of Na2CO3 and H2O in this compound, Na2CO3 10H2O. Now we go to our step 2. Now in our step 2, we're going to calculate the masses of Na2CO3 and also H2O in the raw material. Now in this step, we need to, now that we have the mass fractions of Na2CO3 and also H2O, we actually want to know the masses, the actual masses of Na2CO3 and 10H2 and also H2O in this whole raw material. Remember, we have been given a basis of, according to the question, we have been given a basis of 1000 kilograms of the raw material, which means everything here, including the inert, it's actually 1000 kilograms. So we want to know that out of the 1000 kilograms, how much of Na2CO3 and also how much of H2O is there. That is, the calculating of that is going to help us to figure out all the other information that we're going to need along this question. So let me just write it down, that calculate the masses of Na2CO3 and H2O in the raw material. That is our step 2. Now in doing that, obviously we need to go into choose a basis, and we have been given a basis of 1000. So we say basis is 1000 kilograms of raw material, right? It's 1000 kilograms of raw material. Now with that said, out of the 1000 kilograms of raw material, we can say the mass of Na2CO3, let me just write here that in the raw material, is equals to, remember the raw material is actually 1000 kilograms, and we are told that this compound Na2CO3 is actually 80% of it. So with that, we can just say 1000 kilograms multiplied by 0.8. With that said, this 1000 kilograms multiplied by 0.8 is actually the mass of Na2CO3, including the inerts, which are 20%. So now, out of all of this mass, out of the total Na2CO3, remember we have the mass fractions of both Na2CO3 and water. So we can just say, out of all the mass of Na2CO3, 10H2O, the mass of Na2CO3 can be calculated as, we can actually just use the mass fraction of Na2O3, and we get the individual mass of both Na2CO3 and water, right? So yeah, so the mass of Na2CO3, if you use your calculator, it gives us 296.504 kilograms. Now also the mass of H2O in the raw material is equals to 1000 kilograms multiplied by 0.8, and we know the mass fraction of H2O in that compound then is 0.62937. And if you use your calculator, it gives you 504.496 kilograms. So with that said, we know that the mass of Na2CO3 in this whole raw material is actually 296.504, and the mass of water in this whole raw material is actually 504.496. It's important that I highlight that the water that we're talking about here does not include the fresh water here. It's just the water. Remember, Na2CO3 is actually hydrated. It has water according to the equation, or yeah, the equation of the compound. So that then becomes our step 2. This then takes us to our step 3. Let me just find a cleaner page and just to, yeah, so step 3. Well, let me just write the step 3 here. I think it will be easier. So our step 3, this takes us then to our step 3. Now in our step 3, let's remember that we are told that we have a saturated solution of Na2CO3 at 17 degrees Celsius, right? And remember, the table here does not include 17 degrees. We have 10, we have 20, we have 30, and we want the solubility data of Na2CO3 in water at 17 degrees. So what we're going to be doing to get that solubility data at 17 degrees Celsius is to actually interpolate. So yeah, we'll do that. So our step 3, so we're going to interpolate linearly, to find the solubility. I hope my handwriting is visible. To find the solubility of Na2CO3 in saturated solution of Na2CO3 in water at 17 degrees Celsius. So yeah, so that is actually our step 3. We're going to actually interpolate using this data, and doing that interpolation, one thing that we need to do, remember that we are sure of that, we know the temperature is 17 degrees, but then we don't know the solubility. So to make it a little bit easier, let's define X. So let X be the grams Na2CO3 per 100 grams H2O at 17 degrees Celsius, saturated solution. I hope it's clearer. Yeah, so Let me just put it properly. Yeah. So let X be the grams of Na2CO3 per 100 grams of H2O at 17 degrees Celsius saturated solution. So with that said, we can just say therefore 17 degrees Celsius minus 10 degrees Celsius. Now we are interpolating all over X minus 12.5 is equals to 20 degrees Celsius minus 10 degrees Celsius all over 21.5 minus 12.5, right? Therefore, if you do your calculation, your X will give you 18.8 grams Na2CO3 per 100 grams H2O. So this is actually the data that comes here. When we have 17 degrees Celsius, we're going to be having 18.8 grams Na2CO3 per 100 grams of water. So that actually wraps up our step 3. Now it takes us to step 4. We need to now go to step 4. Yeah, let me just write here that step 4. Now in our step 4, remember that we calculated the mass fractions of Na2CO3 and H2O in this compound. Now in step 4, we're going to be calculating the mass fractions of Na2CO3 and H2O in their saturated solution. Remember, this is just the raw material, and we found the mass fractions and the mass of Na2CO3 in there. Now we go to the saturated solution, and we want the mass fractions of both Na2CO3 and H2O. So that is our step 4. So step 4, let me just write it down, that calculate the mass fraction of Na2CO3 and H2O in, let me say at 17 degrees Celsius saturated solution. So that is basically what we're going to be calculating. We're going to calculate the mass fractions of Na2CO3 and water in here. And for us to go about that, let me just write down that mass fraction. Let's start with Na2CO3 as usual. Is equals to, now for us to actually calculate the mass fraction of Na2CO3 and H2O here, we're going to need this. We can actually use this ratio. Remember, they say for every 100 grams of water, there's 18.8 grams of Na2CO3. So we can actually use 18.8 and 100 grams and add them and make them the total mass, and use both the individual masses, 8.8 for Na2CO3 and 100 for H2O, to get the mass fractions. So with that said, then we can just say 18.8 grams all over 18.8 grams plus 100 grams. Now if you use your calculator, it gives you 0.15825, right? And then the mass fraction of H2O is equals to 100 grams all over 18.8 grams plus 100 grams. Now if you use your calculator, it will give you 0.84175. So that becomes the mass fractions. Let me just bring that. So that becomes the mass fractions of H2O and Na2CO3 at this saturated solution. It's important to understand that when we calculated the mass fractions here, we didn't include the volume or the masses of the inerts. We put them aside, or especially the masses of the inert solids, and we didn't need that because we already had a ratio that we calculated it, which is the ratio of the solubility data here at 70 degrees saturated solution. So with that said, then we are done with our step 4. Then this takes us to our step 5. Let me just write here that step 5. Step 5. Now in our step 5, let me just write down and say, in our step 5, we're going to be then answer the question. Remember, the question says how much of fresh water must be added to the raw material. So step 5, we're going to calculate that water. We say calculate the amount of fresh water added to 1000 kilograms raw material to produce saturated Na2CO3 solution at 17 degrees Celsius. So that is actually their approach. And with that said, for us to get there, I want us to define this as y, because it's going to be unknown. So I'll just write it down that let y be the amount of fresh water added. Fresh water added, right? Now, so now with that said, we then going to do a mass balance. But before we do that, I can just say that at 17 degrees Celsius saturated solution, right? At 17 degrees Celsius, a saturated solution, we have the total, let's say, total mass of Na2CO3 and water. Na2CO3 and water is equals to 800 kilograms plus y. So this is actually the total water here. At saturated solution is actually the total of the Na2CO3 and including and also the water, but excluding the inerts. So this is actually the mass of the water and the Na2CO3, and then we can just say, with that said, then we can actually do an Na2CO3 balance. Therefore, Na2CO3 balance at 17 degrees Celsius saturated solution. So with that said, then saturated solution, we can just say, therefore 0.15. Okay, let me just take the long route. Let me say mass fraction Na2CO3 multiplied by total Na2CO3 plus H2O is equals to 296.504 kilograms. So yeah, that is actually the mass balance. With that said, I can say the mass fraction of Na2CO3, we already calculated it to be 0.15825, and then we multiply by Na2CO3. The total there, we know it's 800 kilograms plus y, right? And then it's equals to 296.504 kilograms. Now with that said, therefore, if you do your calculation, you'll be left with, okay, let me say 0.15825y is equals to 169.5 904 kilograms. Therefore, Y is equals to 1073.643 kilograms. Yeah, that becomes our final answer, and thank you for your time. I hope we meet again in our next video. And I don't think there's anything that is really confusing here, especially if you can just check the look at from here is just the Na230 balance, and we know that in this total 800 kilograms and Y, you multiply it by the mass fraction of the Na2CO3, and that equals to that 296.504 kilograms. So thank you for your time, and I hope to meet you again in our next video. As we're going to be doing, this is actually question A of 2, so we are left with B question